Welcome to Dynamical Systems Lecture 2. During this lecture, we'll continue with our geometric approach with our 1D example. We'll examine the fixed points and then look at some general considerations when doing the analysis. We'll then look at a couple of examples, and finally we'll start introducing a more analytic way of actually analyzing these systems using linearization, and end with some of the fundamental theorems for 1D dynamical systems, which will then form a foundation that we'll later generalize when we go up to higher and higher dimensions. So just to recap, the equation, the 1D equation, our first example that we were looking at during the last lecture is basically x dot equals to sine x. In other words, the velocity field x dot is related to the position by the function sine x. And to just give you, to recap how you would go about analyzing if you got an example like this, draw the x dot or the velocity field on the one axis, draw x on the other, know that your particle is restrained to moving just along the x-axis, and then put in the rule that connects the velocity field with the position. Okay, so here we have our sine graph, and then what we saw was that if you're in this region between 0 and pi, your velocity is positive, so you will increase and move along the axis towards pi. The same thing is true over here. If you're between 2 pi and 3 pi, the velocity field is always positive, so you'll increase and you'll move to that position over there. So the next thing I do, obviously, is simply indicate this by putting in arrows along the x-axis of how your particle will move in response to the velocity field that's been specified. Okay, and I can do the same thing for particles that start in a region where the velocity field is negative. They'll always move to the left, as we stated. So I put in these arrows as well. The next thing I do is I put in fixed points, and you usually mark the fixed points with circles. And in the case where you have a fixed point where the particles seem to run away from, we call that an unstable fixed point, and I mark it with a round circle. And just a bit of, just a suggestion, have a look at the slope of the graph over at this unstable fixed point, because it's something I'll get back to later. Okay, this fixed point over here is basically a stable fixed point. Okay, so sorry, I'm just putting down what I've already spoken over here. So from the unstable fixed points, the solutions run away as indicated by the arrows, and it's marked with an empty circle. These fixed points over here, where the solution runs towards from the arrows, are marked with a solid circle, and they're stable. Okay. And so whenever you analyze another problem like this is basically the convention we use. Okay, and these stable fixed points attract the nearby solutions. Okay. So this is what the phase space diagram looks like. And what we want to do now, and notice the axes are x dot and x, is to be able to sketch the solution in real space as well. And the way that I did it in the very first lecture is you could try and find an analytical answer to this and then sketch the solution. But there is actually a very, very easy way, if you don't want an exact numerical result, to get all the main features of the trajectory in real space simply from clever arguments from your geometry. So let's sketch the trajectory, the same old problem in real space of x of t, as x0 starts at 0 at pi over 2. So in other words, we're going to start over here, and we don't want to view the trajectory as simply moving to pi. We want to know now how it moved to pi. So what we do is we want to sketch the trajectory. So it's x as a function of t. Careful here, it's a different graph from this one, which is the phase diagram graph. This is basically the real space graph. We're going to say x starts at pi over 4. So this point over here is pi over 4. That's x0. And we want to know how the thing changes. So we know one thing, because pi over 4 lies over here, the velocity is positive, Okay, and so the particle x is going to increase. It's going to move that way. But you can also go to that point and you can actually work out the value of x dot at that point, and that will tell you the gradient or the slope of how the graph begins to move away from the point x0. So we know it's going to increase. We can evaluate sine of x0 at x0 to get what the initial gradient is, and we simply put in a line with that initial gradient. Okay, so we know that the graph actually then leaves this point x0 tangent to that line. We know also that here the velocity is increasing, so it's actually going to curve. It's going to get more and more steep, so it's going to curve upwards away from that line. Okay, then it's eventually going to reach, and it's going to continue to curve upwards like this until it reaches the point pi over 2. Okay, so there we put in the graph. The red is now the actual graph. We know that it curves away from our initial gradient all the way till it gets to pi over 2. At pi over 2, it's going to be exactly tangent to the curvature, and you can work out, to the gradient. You can work out at pi over 2, x dot is just equals to 1. Okay, so this is the gradient at pi over 2, it's x dot equals to 1, and here it's exactly, it doesn't curve away from this line, it's in fact the point of inflection, because this is a maximum that x dot reaches. Okay, so that's the gradient x dot. So from then on, it's actually going to start curving the other way. The next thing that's important is we know that ultimately x of t is going to go to pi. We can see this immediately from this graph over here. So it's going to basically start at this point. It's going to move right. It's going to accelerate right. In other words, curve away from the tangent until it gets to pi over 2. It's going to continuously moving right, but it's actually going to start decelerating from pi over 2 until eventually it reaches pi, and it's going to get stuck at pi for all time. So out here, where t gets really, really large, it's simply going to be a constant along pi. And so the natural thing is, whenever we sketch a trajectory in real space, we always put in the fixed points with dotted lines, because they are the points at which the graph either asymptotes or moves away from. Okay, so there's the asymptote as t goes to infinity. And what then remains is we simply draw the graph in. Okay, so we've started with the initial trajectory. We know the initial gradient. We know the gradient at pi over 2 is 1, and that the curve actually changes its bend over there. And we know that ultimately it asymptotes to the value pi. And you can go about and you can do exactly the same thing for any initial condition. And you can now see the power of this approach, because we can draw the graph, which is a very complicated analytic expression, and you can check it without even finding that analytic expression. Okay, so the long-term behavior is simply, in this particular graph, is dependent on the initial conditions. Okay, so every graph where x0 starts in this regime is ultimately going to go to pi. But if you start over here from between 2 pi and 3 pi, you're going to go to a different long-term behavior. Okay, and this thing, the fact that you have it, is a nonlinear effect. Remember, we said that this graph was nonlinear because the right-hand side was not linear. In other words, it couldn't be written as some constant times x. And the fact that the long-term behavior can go to different solutions or fixed points is basically just dependent on which initial condition it starts on. Okay, so think about it. If you have a linear system where x dot is equals to a of x, where a is a constant, it's just a straight line, and you only have one fixed point. So you can either go to the fixed point or run away from it, but you can't. You only end up at one place, either infinity or the fixed point. Okay, and so I want to introduce another concept. It's basically the idea of a basin of attraction for a fixed point. And when you specify a basin of attraction, you have to always specify for which fixed point you are doing it. So for example, if you are considering the fixed point x star is equals to pi, then all the trajectories that start just away from 0 will run there, and all the trajectories that on the left of it, and all the trajectories that start on the right of it, say slightly less than 2 pi, is also going to go there. So the fixed point, or the basin of attraction for the fixed point x star, is simply the region 0, excluding boundaries, to 2 pi. And so that's just another definition I want to introduce at this point. Okay, so it's a very pretty analysis, geometric, very intuitive, that I'm actually going to expect you to do several of these. It's basically gives you the idea of the power of the geometric approach, where we can actually analyze this equation without analytically integrating the differential equations, and we can get a complete picture of what the trajectories look like, even though we don't have the analytic answer. In fact, we can get a more complete picture because we get a feel for what all the initial conditions do by simply looking at, remember, this is called the phase space diagram. Okay, so now in general, I just want to recap the 1D analysis. So it goes as follows. For x dot equals to f of x, so where f is now an arbitrary function, draw the phase space diagram of x dot versus x. Draw the graph of your velocity field f, so it can be anything. Okay, so these are the steps you're going to go through for any analysis, 1D analysis like this. Then the next thing is find all the fixed points, and there they are. Okay, I've just made them empty circles for now. We're going to start identifying whether they are stable or unstable the moment we've put in the arrows. Okay, so the fixed points simply satisfy the case where f of x star is equals to 0. It's the zeros of this f function. The next thing is draw in all the flow directions. In other words, where the graph is positive, put an arrow to the right on your x-axis. If the graph is negative, put an arrow to the left. Okay, so here are all the ones that flow right, where the graph is positive, over there and there. And here are the ones that flow left, there and there. And once you've done that, you can immediately identify the stability of your fixed point. So this is a stable fixed point where the arrows point towards, and this is an unstable fixed point. Okay. And we can then fill it in. So unstables, remember, are empty circles. Stables are filled circles. And this other one, this other one is also an unstable fixed point. Okay, so I'm now going to do one more example that also gives you an idea, and I'm going to use this example as a jumping off point for another concept I want to illustrate. Okay, so the next example is the logistic equation. It's basically x dot is r times x times 1 minus x over k, where r and k are actually constants. So this is basically illustrating what happens if we put parameters into our equation. And so our analysis is the same. In fact, here we simply, the only thing that's getting more complicated is we're no longer dealing with explicit numbers, but we're dealing with somewhat more abstract parameters. So the first step is, once again, sketch the graph of x dot equals to f of x. We can see it's quadratic in x. There's a negative in front of the x squared term, so it's an upside down parabola. And we sketch it simply by finding the turning point, which is when x dot is equals to, the derivative of this function is equals to 0, and that occurs at k over 2. We also put in the 0 points, in other words, where x is equals to 0 and x is equals to k, okay, and then we immediately can put these values, always put the actual constant values on the axes, because it makes it easier to analyze a thing, even if you don't know what the constants are. And then the maximum occurs, remember, where ddx of this f of x is equals to 0 at k over 2, and then we also put in the maximum values. So when x is equals to k over 2, f of x is equals to rk over 4. Okay, so those things are important if you're dealing with the equation with parameters in. Sketch the solution with the parameters actually on the axes. So we now draw the flow directions, and there they are. If the graph is positive, the arrow goes right. If it is negative, the arrow goes left. We put in the fixed points. So we have an unstable fixed point over here because you can see the arrows move away. You have a stable fixed point over here because you see the arrows move towards it. And then we have, if you look at the solution, is that all the solutions move to the point x star equals to k as time goes to infinity, provided you start with x greater than 1, or sorry, greater than 0, right? This, if you start over here, it's going to run away to negative infinity. But if x is greater than 0, it's all going to go to k. And the interesting thing is this equation comes from population biology. So x actually represents a population over here, and therefore x is always going to be greater than 0, and this is why I made this statement. So strictly speaking, I should have put x greater than 0 over here if I didn't tell you it came from biology. Okay, but here I do. So the origin of this equation is population biology. It's an equation that we're actually going to that's going to appear in several places. It's a very simple equation that actually illustrates nonlinear behavior, and many other models that we build are going to have the same foundation equation. So it's worthwhile to get to know it a bit. Okay, so the origin of this equation is population biology. X represents the population of organisms. For example, if you're looking at the growth of COVID, say, or the growth of rabbits in a certain environment, or sheep, or whatever, x dot is the growth rate. R is the initial growth rate. Okay, so that's a constant. That's basically how rapidly the group of animals can reproduce. And that's usually set by the gestation period. So if it's mice, it's very rapid. If it's elephants, the growth rate will be very slow. If it is dassies or hyraxes, the growth rate will also be very slow because those poor little creatures have the same gestation period almost as an elephant. K is the carrying capacity of the situation you're looking at. So the carrying capacity is basically how much food there is available. So, for example, if you have all your sheep in a field, there's only so much grass they can eat. And once you have too many sheep, the grass disappears and the sheep die. So that basically sets the point at which the maximum amount of sort of population that environment can support is the carrying capacity. And therefore, you can actually see that what this equation predicts, if you have a positive population, is that it's simply going to run away. It's going to start anywhere. The animals are going to increase with a certain rate, and then eventually it's going to go to the carrying capacity of the environment that you're in. Okay, so just one thing over here. If k goes into infinity, x dot over x approaches r. So that's what I said, is that if k goes to infinity, if the carrying capacity is much bigger than the population that you have, then the sheep are simply going to breed as if there's nothing, and you're going to have exponential growth rate. And this r value is when everybody speaks about COVID's growth, right? The carrying capacity for COVID is basically the whole world's population, and it's much bigger than the individuals in a population. So initially, COVID used to grow with this R0 value that everybody speaks about. And in fact, this is the same R value that appears in this equation. So if the carrying capacity is large and your population starts out, it's just going to do exponential growth, which is what everybody's so scared of, and which is the reason why we do lockdowns. But that exponential growth is exactly what we're seeing over here as well. Okay, so the models that model COVID are more complicated than this one, but this part is also in that model, and the R value is the initial growth rate that you have. Okay, so if the carrying capacity is large, x of t is simply going to obey this equation, and if you integrate it, you have that x is equals to x0 e to the rt, which is exponential growth, which everybody is so afraid of. But the truth is, any animal that reproduces or virus that reproduces and starts growing, or even bacteria, that reproduces and starts growing and starts small in a small population is going to have an exponential growth, and it is going to have an R value. Right. So when it gets interesting is, so initially the thing is going to grow very quickly, and eventually the growth is going to slow down until it eventually reaches the carrying capacity. So let's see this explicitly, right? We now want to plot, once again, just as we did in 2 slides back, we want to plot our actually population value for various initial conditions to see how it works. And so what we do is we don't have explicit numbers here, so we actually can do it in terms of the constant that's provided, because remember, we're not actually getting explicit answers out. We simply are getting a feel from the trajectory from the graphical methods. And so you can sort of illustrate the power of this form of analysis. So here is our physical space. X is a function of t. We immediately put in all the important values for x. So we look at our phase diagram graph over here, and we see that the important things that appeared was this maximum, where your f of x basically turns over, reaches its maximum point. The other important point is the fixed point. And remember, the last time we plotted the physical space, I said always put in the fixed point. So here it is, because the fixed point is the line to which the solution asymptotes, right? And this k/2, where the maximum of the graph is reached, this point over here is, remember, the inflection point of the graph, where it changes its bend from the one direction to the other direction. And the 1/r we've put in because it is it is basically the only time scale in time. And you can see from it here, when we look for the exponential growth, initially we saw that the factor RT enters into the expression. And so when this thing is 1, okay, time is equals to 1/r, and this is why we put the 1/r in here. It's basically, it sort of gives you an estimate of when you have moved out of the exponential growth phase. So we plot in the asymptote, okay, and we write down what it is, just to help things, because some of these graphs get quite complicated. So this is the solution asymptote as t goes to infinity. So we know our solution, if we start with x greater than 0, is eventually going to end up here. And now we put this, I put in the second one, which is basically the inflection point where the graph changes bend, because it just helps me, makes it easier for me to actually draw the trajectories that come in. And so at the bottom here, let's draw one of the trajectories. We pick any point, and if it's close over here, initially the initial slope is going to be just the value on the graph, so it gets smaller and smaller the closer you go to x equals to 0. So it's almost flat over here. It bends away from the initial slope until it goes up and it hits the inflection point. Then it basically changes its bend as an exactly tangent to the slope over there, which is basically rk/4. And then it bends the other way until it approaches the asymptote. Let's put in another one. As you go, increase your initial point. So you're starting at a greater x dot value. You can see the slope here increases, right? It's a bigger slope, but it still bends away from the initial slope until it reaches the inflection point, bends the other way, and then approaches the asymptote. You increase it still more until it gets close to k/2. It starts over here until it reaches asymptote, bends the other until it reaches the inflection point, bends the other way, and asymptotes to the k value. If you start on this side, it's never going to reach an inflection point, right? It's already bending, it's already decelerating. So it's already curving towards the asymptote, and you can just draw it approaching the asymptote. If you start on this side, it's once again, the slope is negative. So that initial slope is negative, and it just bends towards this asymptote. Okay, so I expect you to be able to draw these graphs of the physical space by simply looking at the phase space diagram, just as I've explained now. Okay, so let's put in a few more. And once again, you see the power. We haven't got an analytic solution for this problem, although there is one, but we are able to draw all the trajectories and get a very good estimate for x as a function of time simply by knowing the features of the phase diagram over here. Right, so now we've got a good introduction to the graphing methods. Let us add another technique, and that technique is linearization. So the idea behind this technique is we know that all the interesting stuff happens at the fixed points, okay? And what we're going to do is simply examine the equation very close to the fixed points and see if we can learn anything. Remember, a little while back, I told you that look at the stable fixed points, look at the slope of the graph of the stable fixed points, look at the slope of the graph of the unstable fixed points, because you might notice something. And now I'm simply going to derive what I hope you noticed in those graphs. Okay, so the aim is basically in linearization is to examine the dynamics of x dot equals to f of x, your equation, close to the fixed point x star, and x star is defined as the position at which f of x star is equals to 0. So a specific graph might have more than one x star, but we just pick a specific one. And the way we go about that is we say let x of t be equals to x star, our fixed point, plus another function eta of t, which parameterizes its departure from x star. And eta is usually assumed to be small. And then we want to work out the derivative, because that's what enters into this equation. So you work out x dot is just ddt of x of t, so it's ddt of this thing. So it's ddt of x star, but x star is a constant, so that's going to be 0, plus ddt of eta of t. Okay, so that simply equals to eta dot, right? So x dot is simply equals to the velocity of your deviation. And then what we're going to do is we're going to expand f of x about x equals to x star. So we're going to do a Taylor expansion, and the way we do that is simply to use Taylor's theorem, and what we get is that the first term is simply the function evaluated at x star plus eta times the derivative of the function of x star, plus you can go order high order terms where you have basically 1 over n factorial multiplying the nth derivative of the function evaluated at x star. And so the nice thing here is this f of x star is equals to 0, so we're simply left with the fact that f of x is equals to eta times f of x star. And f derivative at x star. And f derivative at x star, remember, is just a constant, right? Plus the higher order terms. But what we're going to do in linearization, which is why we call it linearization, is we're going to assume that eta is small and that we can neglect these higher order terms. So what we then do is we keep only the first order term, and we substitute this expression of f of x into this equation. Okay, so we basically put f of x is approximated by eta times some constant on the right hand side, and x dot is equals to eta dot on the left hand side, and we're left with this. Okay, so it's very important to remember that this f prime of x evaluated at x star is a constant. Okay, so it's a number, and we're going to call that number r, strategically labeled just like we saw with the exponential growth. And we can now see that our linearized equation is once again just a linearized equation for exponential growth. And so we can have that if eta grows if r is greater than 0. Okay, and what does that mean? If eta grows, the deviation from x star gets bigger, it means your fixed point is unstable. In other words, solutions are going to run away from that fixed point. If eta decreases to 0, if r is less than 0, which means that x star is stable. So if r is less than 0, it basically means that your solution is eta equals to e to the minus or a negative value times t, so it's going to shrink to 0. So if you move away from the fixed point, you're just going to come straight back to it. So that means your fixed point is stable. And if you have r equals to 0, you can say nothing, because you have to look at higher order terms. So your analysis is inconclusive if the derivative at the fixed point is equals to 0. Okay. And in that case, you actually have to look to higher order ones, and we'll give you an example in one of the problems that actually illustrate how this happens. So if the derivative is 0, then just know you can say nothing. It can be either stable, unstable, or half stable, and we'll show you the examples. But in the other cases where the derivative is either positive, the graph is unstable, or if it is negative, it is stable. Okay. And if it is 0, then you actually must look at the graph to see what's going on. And so these facts, that the derivative being positive, indicating that the graph is unstable, if you go back at all the graphs we've drawn so far, and you see that if the slope is positive, the solution tends to run away from that point, and if the slope is negative, it tends to be attracted to that point. It's exactly consistent with the results that we got when we drew arrows onto that graph. Okay, so let's just have a look at an example. Once again, we're going to go back to the logistic equation. Here it is, okay, and with our constants, and we're going to say the fixed points satisfy x dot is equals to 0, and this occurs at x equals to 0 and x equals to k. And what we now want to do is examine the stability. So remember that I've just said that if f of x star is negative, then x star is stable. And if it is greater than 0, then x star is unstable. And so let's see what we can get from this test for this logistic equation. So the first thing is you have to work out the derivative of f of x. Okay, so you just take d dx of this thing, and that's equals to r minus 2rx over k. And then we evaluate that at each fixed point. So if f derivative at 0 is simply x equals to 0 is just r, and r is assumed positive because it's a positive growth rate. So 0 is unstable. Okay, which is consistent with what we found. F derivative at k is equals to this expression. If we substitute where we've substituted k in for x, these two cancel, so we're left with it being equals to minus r, which is negative. So f of x equals to k is a stable fixed point. Okay, and if we now compare this result that we can now get just purely analytically with the graphical method, here is it's exactly what we saw from the graphical method, right? Here, where the slope is positive, the solutions tend to run away, so the fixed point is unstable. Where the slope is negative, the solutions tend to run towards it, so it's a stable fixed point. So we now have two methods to actually determine whether a fixed point is stable or not. The one is the graphical method, and the second method is the one that we do by means of linearization. Right. Okay, so the final thing is that I just want to give you a few theorems about, or basically all the properties of 1D equations that we can actually infer from our discussion we've had so far. So the first thing is, I'm not actually going to prove, because you were meant to prove it in the second year, is that for the solution, for the equation x dot equals to f of x, you have that solutions always exist and that they are unique. Okay, so there's a theorem that states that the solutions x of t exists and are unique if f of x and f prime of x are continuous in x. And this is reasonably straightforward in this case because it's simply just the fundamental theorem of calculus that you can always find or sort of work out the integral. And you can say that you basically have dt is equals to x over f of x, and you can always integrate a function, and therefore the solutions exist, and the integral is unique as well. Okay, so this theorem holds. The second theorem that we have, and it comes from the graphical method, so I've just put up the picture over here, is that we can, from this existence and uniqueness, as well as what we know about the graphical method, we can actually say more about the solutions. We can say something about the nature of the solutions. And what we can say is that the only possible long-term behavior for these solutions of x of t is either to approach a fixed point or to approach infinity. Okay, so any possible long-term behavior of a solution to this equation, x dot f of x, is x of t approaches x star monotonically. So there may be more than one fixed point, but it is going to approach a fixed point monotonically. Or it is going to approach plus or minus infinity as t goes to infinity. Okay, and so this thing is very restrictive on the nature of the possible solutions we have. And in particular, what it means is that it's impossible to have the following situations. So in one dimension, it's impossible to have something that oscillates. Okay, because that would violate this first one, is that it approaches a fixed point monotonically. So it's impossible to do this. And the reason is that if you start here, because you're simply restricted to moving along this line, you can only increase if x dot is positive, either monotonically, or you can decrease if x dot is negative, also monotonically, but you cannot oscillate. So this is not allowed for equations that obey, or solutions to this equation. The second thing is you can't have oscillations, right? You can't have the function oscillating, and that's for exactly the same reason. It has to move monotonically. So if you think back of the graphs we drew for the logistic equation and for that other example, the sine example, all of them sort of just simply started at a point, went through a point of inflection, and then went to an asymptote, and that's the only thing that is possible. So it's a very restrictive theorem of the type of solutions you can get in one dimension. And you'll see in the subsequent lectures, to have oscillations like this in x of t, you actually have to have your equation being a solution to a higher order, or at least a second order equation. Okay, so I just want to write that out. In one dimension, the fact that your motion is restricted to move along x, the x-axis, in other words, the topology of a line, basically restricts the possible dynamics to so that they're only monotonically increasing or decreasing. Thank you very much. This is the end of the lecture. Please go through the material by yourself, as well as trying a few of the exercises I'll also upload. Until next time.